So hi everyone. So my name is Youssef, and I am a cryptographer. I work at EY, Ernst & Young. So today we're going to talk about elliptic curves in cryptography in general. But since the presentation is about, the meetup is about zero knowledge, at the end of the day we're going to talk about elliptic curves in zero knowledge proofs. So just to have a sense of the audience, does anyone who doesn't know what are elliptic curves? It is similar to a story we all know. So it's going to be a story today of the story of humans. So the story of life, how it started. So the Big Bang will be the creation of elliptic curves. So we're going to talk also about before the Big Bang. So what was happening before we discovered those elliptic curves. So post Big Bang, the mathematical foundations. So biodiversity, is there only one elliptic curve or many? So biodiversity in which sense? And then, so what I call the homogeneous is, so this specific species that is elliptic curves in cryptography. And so, yeah, fire control is, so one of the main discoveries in human life is the control of fire. So when we control what I call pairings or bilinear maps in cryptography, so we could do first some destructive use and then some constructive use, just like fire. So there are a lot of similarities we're going to go through, but mostly it's going to be technical. So, yeah, so just let's start by what was happening before the Big Bang, before the creation of elliptic curves. So we will start with something very easy, that is a circle. So everyone knows what is a circle. So this is the equation of a circle. So in affine coordinates, in polar coordinates. So if I ask you what is the area of a circle, it is pi r squared. What is the perimeter? It is 2 pi r. So ellipses are somewhat a generalization of a circle. So this is the equation of a circle. So those equations are centered. So the origin is 0, 0. So if I ask you what is the area, it's going to be pi I AB. So you can ask me questions of the fly if you want. Pi AB, so it is somewhat pi r squared. So we have only one radius in a circle, but in an ellipse we have two radius. So the major axis and the minor axis. So it is like AB. So if A is equal to B equal to R, so it is the same. So if we take a look at the perimeter. So it's going to be different. So how can you compute a perimeter? So you compute the arc length, you integrate over so the arc length. So in the circle you have 2 pi r, but if you want to compute the integral in an ellipse shape, so you will have this integral. So that you cannot solve. So first, just historically, it was the circumference of an ellipse was described by series, by Newton, Euler, and Maclaurin. But then Adrien Marie Legendre, so he expressed the perimeter with this integral. So this is, by the way, what we call an elliptic integral. So of the second kind, I guess. And after that, Abel and Jacobi, so they studied the inverse of this integral. So the inverse of this integral turns out to be doubly periodic. And even the derivatives are doubly periodic with the same period. So it satisfies differential equations. So if you put x as this elliptic function, so elliptic function is the inverse of elliptic integral. So we have a parameterization known today as an elliptic curve. So this is just before the creation of elliptic curves, because one of the questions we ask is why it is called elliptic even if it has nothing to do with ellipses. So this is like the explanation. So once we have those elliptic curves, so for example, this is what we call, and we use in cryptography, for example, we mostly use in cryptography, it is this Schwarz-Weierstrass elliptic curve. So y squared equal to x to 3 plus ax plus b. So we need to verify some conditions with respect to a and b, because to avoid some singularities in the curve. But just take the elliptic curve as this equation. So we are working on some arbitrary field, but that have some conditions, but this is like the elliptic curve we found if we Google an elliptic curve. So, so here I'm just giving some information about how we can characterize this elliptic curve, so the J invariant, but we're gonna talk about this later. So now we have elliptic curves. So we define a law on this elliptic curve. So here an addition law. So if you take 2 points on the elliptic curve and you want to compute the addition of these 2 points, so you just trace a line that passes through the 2 points, and the intersection with the third line is the inverse of the point. So you take the intersection, the third point, and so just like in this figure, so it gives you minus r. So the opposite with respect to the x-axis is the third point. So we were just explaining how things works to come to the point that how you can generate your own elliptic curve, for instance. So here just some special cases we have to handle. So the points, the neutral point. So it is in the projective geometry, not on the affine plane, but just like it is a point. If you add this point to 0, it will be the same point. And the most importantly, if you add points, a point to himself. So you double this point. So just intuitively, you can do the proof analytically, but just intuitively, if you have 2 points and then they come to each other, so if it is the same point, it will be a tangent. But then you can prove that, so you have a line that is an equation of degree 1, you have an elliptic curve equation of degree 3. If you do the intersection, you will have an equation of degree 3. It has 3 solutions, or maybe 2 or 1 with multiplicity. So if it has to, it has to be a tangent. So now that we have well defined our addition law, so if you Google an elliptic curve addition law, so this is like the geometric interpretation. So we understand how it works, but then you need to find those algebraic formulas. So when you Google them, you just find those formulas, but just to explain where do they come from. So you have an elliptic curve. So this is the equation. You have a line. So a line or a tangent. So it has the same equation, but the m and n are different. And you are looking for the intersection point. So you are looking for the intersection point. If you substitute the line in the elliptic curve, you will find out this equation. That is an equation of degree 3. So if you want to find the point, you have to solve this equation. But since you have already 2 solutions that are the 2 points that created the line, so Vieta's formulas tells you that the sum of the solutions, you can express them with the coefficients of the polynomial. So you have this, so the algebraic formulas of the addition. So this is what is implemented when you use elliptic curves. So in addition of this law, that is addition law, we define also the law of scalar multiplication, that is adding the point to itself n times. So this is like the most important thing when you use elliptic curves in cryptography, is that if you add the point to itself n times, so you do the scalar multiplication of a scalar n times a point, you will end up with a point on the elliptic curve. So this process is pretty much straightforward in a sense, but then if you want to go back, it is hard. But when you explain it this way, so one natural question to ask, so if you do n times p, so you add p n times, so you will need n minus 1 additions. So if you need n minus 1 additions and n has, for example, k bits, so the complexity is 2 to the power k. And knowing that in cryptography you use big numbers, so 256 bits, for example, so it is harder to do this process. We said it is pretty much straightforward in a sense. So instead of doing this, you do some nice tricks. So the most basic one is double and add. So it's based on the Horner rule. So if you can express a scalar into a binary decomposition, you can do double and add. So if the bit is 1, you do doubling, you do addition, and then you do doubling. So this is like the very basic algorithm in order to do scalar multiplication on elliptic curves. but it is vulnerable. I mean, you use the algorithm depending on the purpose you want to achieve. For example, one easy attack on this algorithm is timing attacks. So for example, we have explained that you have different formulas in addition than in doubling because the line is not the same, so it is a tangent in the doubling. So timing attacks is just you compute the time to do a doubling, you compute the time to do an addition, and then you guess it. This time is 1, this time is 0, so you can reconstruct the secret, the scalar, just with the timing consumption. So you can solve this by some other algorithms. So I've mentioned some few here. So yeah, for example, fixed or sliding windows, you can leverage on pre-computation. You can compute 2 to power w times the point. So you can have a window fixed or sliding. You can do so non-adjacent form methods. For example, we said that the opposite of a point is just the opposite with respect to the x-axis. So if you have a point xy, it is x minus y. So negation is somewhat free. So if you can, rather than using binary decomposition, use NAF decomposition, that is with 0, 1, and minus 1, and you leverage on the fact that minus 1 is free. So you will have more zeros, and then it will be quicker. Yeah, and the last one is another thing, GLV or GLS methods. It's when you find some elliptic curves that have faster endomorphisms, but we can talk about this like in Q&A. Or maybe you can change the shape of your curve to use a Montgomery curve or an Edwards curve that have some other nice tricks. We're going to talk about them, I think, in 2 slides. So no questions?
Question?
Yep.
What represent in the scalar multiplication?
Yeah, n is a scalar. So for example, if you have a point P, you are... For example, in blockchain, it will be the secret key. So yeah, if you have a pair of keys, so in Ethereum or Bitcoin, you have your secret key, it is this scalar, and your public key is based on NP. So it is the hash of NP. So in Ethereum, it is the hash and 160, the last 160 bits in Ethereum. So yeah, biodiversity. So yeah, once we have defined this elliptic curve and so how you can define laws on this elliptic curve, so you have many species that raise from elliptic curves. So yeah, biodiversity with respect to fields. So if you define the elliptic curve on some specific field, it's gonna be different. So for example, in elliptic curves over the real numbers, so it is the picture on the top left. So if you Google an elliptic curve, this is usually what you get. So this is an elliptic curve over R. It's not the elliptic curve we use in cryptography. So over C, for example, it is a torus. So this is the mathematical term for a donut. Or if, for example, over rational numbers, we cannot picture it because, as you cannot picture Q sitting in R. And over the integers as well, we use all of these, for example, in construction in elliptic curves, especially over Q and over Z as well with Siegel theorem. And then the elliptic curve in cryptography is over finite field. So this is the one at the bottom left. So these are the elliptic curves we use in cryptography. So I just mentioned some theorems and conjectures in elliptic curves over. So it is mainly over Q. But this is just to say that if you define elliptic curves over a specific field, you will have like some different constructions. So this is the biodiversity with respect to fields. You have also the biodiversity with respect to shapes. So so we presented first the short Weierstrass form because we can prove that every elliptic curve is isomorphic to the short Weierstrass if we are working in a field that has characteristics different than 2 or 3. But the idea is you can always reduce this elliptic curve to generally in short Weierstrass. But then you have also different shapes. So you have, for example, the normal Legendre. You have Montgomery, you have Edwards, you have Jacobi quartic, Jacobi intersections, you have Hessian, you have Icard's Kohel. Well, it depends on the purpose you want to achieve. For example, if you want faster arithmetic, maybe you will go with Montgomery or Edwards. If you want unified formulas, so you need those formulas to be the same whether you are doing doubling or multiplication, because I remember, or addition, because I remember we had different formulas in Weierstrass, so you will go with Edwards. If you want less memory, you will go with twisted Hessians. So the idea here is you have a biodiversity of shapes, and everyone is used, for example, in cryptography for a very specific purpose. And then you have also biodiversity in coordinates, so we have only defined curves over a fine plane. You can also define them over some other kind of geometry, so mainly projective geometry, because if you remember this, so we have inversions, and we do not like inversions in computer science. So what you can do is you define this third coordinate z, and then you define it to be like the common denominator. So you will have maybe more multiplications and additions, but you will have no inversions. Those are some coordinate Jacobian. I think it is the best in Weierstrass, Lopez de Haave if you are working in characteristic 2, inverted in Edwards. And by the way, the one at the top right is a Hessian. This one bottom right is an Edwards, and the other one is a quartix, is a Jacobi quartix. There is a link here of Daniel J. Bernstein and Tanja Lange that gives explicit formulas for every specific shape, every specific coordinates as well. So now that we have this biodiversity of elliptic curves, so it was introduced like many years ago, but they were introduced in cryptography at the end of 70. And it was introduced on, so just like our story of humans, the main species is homogeneous. So we will call this a Homo sapiens. So this is the elliptic curves over finite fields. So the elliptic curves over finite fields. So why we use finite fields? So this is like in cryptography in general, we always use finite fields because, well, very intuitively we would like things to be infinite in cryptography, so that we have many probabilities. But in computer science, we do not like things to be infinite because of storage. So what we do is we use some finite fields, but infinite in some sense. So finite fields are just cyclic. So if you take a finite field of 3 elements, so it is 0, 1, 2. But then if you take 4, it is also 1. If you take 5, so it is infinite in a sense. So this is I took the short Weierstrass elliptic curves we have proposed. So it is, so the finite field is, the elliptic curves over finite field form a group. So one of the questions is how many points are there on the elliptic curve? So how many points are there on the elliptic curve? So if you tell me that x is between 0 and p minus 1, if we are working in FP, so you just need to replace and then solve the equations of the elliptic curve, but then it is not, it's not in polynomial time. So we have Schur algorithm that leverages on Haas theorem, Frobenius endomorphisms, and Chinese remainder theorem. Just for example, so we are asking how many points are there on the curve. So instead of proving Haas theorem, very intuitively, so you have an elliptic curve. You need to compute how many points are there on the elliptic curve. So you need to solve this equation. So imagine that for every x, you have a y. So you have at the end, so px, so you will have p pairs xy. plus the point that is not on the affine coordinate, so the neutral point. So you will have p plus 1. So this is in the case that for every x you have one solution. But since it is a quadratic equation, you will have maybe 0 solutions, 1 solution or 2 solutions. So this is like the p plus 1 minus this, what we call the Frobenius trace. There are many ways to define the Frobenius trace, but this is one of these ways. And we define a cyclic group, that is, if you take a scalar, so with the equation we have defined, and you times a point, if it is equal to 0, so it is a subgroup of order n. So all of this to come to the point to how we can use elliptic curves in cryptography. So yeah, so this is what I call Homo sapiens, but let's do not forget that there was before Homo sapiens some cousins called Homo erectus. So the history of cryptography was mainly at the very first symmetric cryptography. So you need to do encryption. So you have a message you want to encrypt. So you encrypt it with a key, and then to decrypt it, you decrypt it with the same key. So this is a problem because you need to store very securely your key, because the one that do encryption does decryption as well. So then there was this new notion of asymmetric encryption. That is, the key that does encryption is not the same that does decryption. So it was first introduced in finite fields, not in elliptic curves. So the idea is just you need mathematically to find some problems that are easy in a sense, in a way, and difficult in the other way, computationally hard to be exact. So if you take 2 points, two numbers, for example, 2 prime numbers, and you want to do the multiplication, it is very easy to do the multiplication, but to do the factorization, it is computationally hard. So the best known algorithm, for example, runs from the index family, so it is the general number field SIP, and it runs in sub-exponential time. So here the idea was we wanted to find some other groups that are generic. So we say that are generic in the sense of Victor Shaw. So that are generic, that means whatever the group you are working on, the best attack will be the generic attack. And the generic attack runs in quadratic complexity. So we call road polar or baby step, giant step. So this is where we introduced in cryptography elliptic curves. So we introduced elliptic curves in order to have the same problem, because we call it as well the discrete logarithm problem over elliptic curves. But what is a logarithm in elliptic curves? It's just analogy with the discrete logarithm over finite field. So if you have a, b, k, it is computationally hard to find k given a and b to the power k. So so yeah, so this is like the cousin of our. So once we have defined all of this, the question is, how can you create your own elliptic curve? Because, well, so for example, everyone who uses elliptic curve cryptography knows what is ECDSA or ECDSA, so key exchange or digital signatures. But let's remember that the first paper that was introduced elliptic curves in cryptography, it was by Kovlitz, and it was more about encryption. But we do not use encryption. If you Google encryption with elliptic curves, you will find some hybrid constructions with elliptic curves. You just create some secret with ECDHA, and then you use some symmetric cipher. But the point is why we do not use this, because we need to hash plain text, the message you want to encrypt, into a point on the elliptic curve, and so given this way, it's not easy to find some good construction. So in the paper, what he proposed is you take the message as the x coordinate, and then you need to find the y coordinate. So first you need to solve a quadratic equation, a modular quadratic equation. So we know how to do this via what we call Donnelly-Shanks algorithm. But the point is, what if there is no solution? So you need to find some padding protocol in order to change your x in order to find a suitable y. So yeah, so now that we want to create our own Homo sapiens, our own elliptic curve, so with respect to all what we've seen so far, so you need to find a shape. what shape. So it depends on the purpose. So if we stay generic, so let's say Weierstrass, it is the simple form. You need to find a field. So the field, when I say the field, so where is the P and in which characteristic? And you need to find the order. So the order defines your security. For example, in cryptography, what we do is we fix the security. We say, I want a security, let's say, of 128-bit. That is, I cannot find the secret in less than 2 to the power 128 operations. And then I will see what are the parameters. So with respect to the attack, we've seen root polar that runs in quadratic complexity. So I need an order that is 256 bits in order to have 128 security level. I want also the ratio between P and the order to be small. I mean, I do operations on this group, but let's do not forget that the X and Y coordinates of the point are on the FP. So I do operations on both arithmetics. Do I want the order to be prime or not? So these are attacks, for example, if you have composite order. So an attack last year in Monero used elliptic curves that have composite order. And then I need, of course, to find my coefficient. So if I define my elliptic curve at Weierstrass form, so what is the A and B, for example? I need to find, to specify the Frobenius trace, the T that is in the order of the group. So why? Because we know that for some specific cases, the security of the elliptic curve is not good, because, for example, if T is equal to 1, we know the discrete the problem is very trivial, so it is an additive transfer. So yeah, we call it the 4S attack, but I think the first one was NIST when he was working at HP. So it is an attack that uses some periodic transformation, but the idea is just the discrete logarithm is easy. If T is equal to 0, you will find that it is a very specific elliptic curve called super singular, and it has some security concerns as well, and some other conditions. We will explain them when we will talk about pairings, but yeah. So let's take an example. So I think that this is the elliptic curve, the most famous elliptic curve. So NIST P256. So I think that everyone used this, and we will try to understand why it is used, why it was standardized, and from where do all those elements come from, except the one in red, we do not know. So NIST chose an elliptic curve of Weierstrass form. So it is y squared equal to x to 3 plus a x plus b. So it is a Weierstrass curve. So the first question is, so we do arithmetic over p. So they chose a prime number that has this form. So it is a very nice prime because we call it Solinas prime with respect to the paper of Solinas, or generalized Mersenne number. So if it is 2 to the power something, it is very CPU friendly. The order has to be 256-bit if you want the security level to be 128. And then comes the question of the A and B. So in cryptography, there is what we call nothing up my sleeve. You always want to prove that there is no way you could have put a backdoor. So if you propose some elements A and B, you need to tell where do they come from. So for the A, it is honest. A, they took A equal to -3. Why? Because for a very specific reason I put there. When you do addition with the equation we showed, if you do them in some projective geometry, so with some other coordinates we call Jacobian, you will have an intermediate step, that is this one, m. So if A is equal to -3, you can reduce computation. You can reduce computation because you reduce the computation in the multiplication by I, and you reduce two squares. So you would have done x to 2, z to 2, and z to 4. Now you do only z squared. So this is very honest. But the B, we do not know where it comes from. So the B comes from, they say they hashed a seed, but we do not know where this seed comes from. So this is why many people think that we should not use NIST curves. So it's up to you. But then all the security conditions we have mentioned are fulfilled. I mean, we check the Frobenius trace. It is not equal to 1, not equal to 0. The discriminant, so yeah, the discriminant, if the discriminant is small, we know how to speed row polar, the best attack, but it is very well understood. So, and for example, in pairing-friendly ellipticals, we want D to be small, but it is like a trade-off. Yeah, and also another thing, when you assess the security of an elliptic curve, you have to assess the security of all the isomorphic elliptic curves to this one. And by isomorphic, you can always, for example, in short Weierstrass, reduce it to the short Weierstrass. But if they are isomorphic in another field, so this is what we call twist, you need to assess the security on this twist as well. So yeah, you can prove that if your A and B are both not equal to 0, you will have only one twist that is quadratic. So you have only to assess the security in only one twist. So I checked the cofactor of the twist, so on the security of the twist, it's fine. So the only thing here is the seed, where does it come from? So this is why, for example, in Bitcoin or blockchain or Ethereum, they use another elliptic curve called SecP 256K1. And yeah, so now that we have, for example, a standard elliptic curve, why in Ethereum, for example, you use other elliptic curves like BN or in Zcash BLS, or in, for example, in Monero curve 250 to 5519. So it depends on the shape, on the arithmetic you want to do, but also to some, so why I called here in the presentation, fire control. So the idea here is, well, fire as it wasn't about discovery of fire, but it wasn't about controlling and mastering fire. So, for example, those humans here, so they knew probably what is a fire. So, I mean, they've seen a fire devastating a forest, for example. But the point is, how can they produce a fire? How can they control a fire? So, and once they have controlled a fire, they have probably used it in a destructive way to attack animals, to attack each other, to protect each other, and then they have used it in a constructive way to bring warmth, to bring light, to cook food. So this is the same story with pairings. So pairings were discovered by, André Weil. I think, yeah, it was the first pairing where he was in jail in France because he refused to serve the French army during the Second World War. But then he discovered the veil. And in his autobiography, he wrote that after getting out of the jail, he wrote to the head of the French Academy of Mathematics to ask him to put all the mathematicians, French mathematicians, at least 2 years in jail because it is productive. Yeah, a pairing is very difficult to explain, but we can treat them as black boxes for now. So they are bilinear. So you take two elements from the elliptical, from a group of a specific order on the elliptical, and it gives you a point on another target field. Okay, so they have to be bilinear. So if you have a combination of the elements in the left, so you have a combination. So E of P plus RQ, so they are bilinear. They are non-degenerate, so this is like the big problem. So this is all about controlling, is this non-degenerate or strongly non-degeneracy, and they have to be computable. Yes, so I've done an illustration example with some pairings that has nothing to do with this, but you just have two vectors U and V. You compute the determinant of the matrix formed this way. So the big point here in red is alternacy. So if you compute the pairing of an element with itself, yeah. I'm sorry. Line 1, yeah.
Line number 1. T is between square P minus 1 and square P plus 1.
T is between minus 2 square p and plus 2 square p. Yes. Yes. Yeah, it is the Frobenius choice. Yeah, it is the same T that I have in the other slide. Yeah, it is between minus 2p and plus 2p. Yep.
The Laurent described problem in elliptic curve and the Laurent described in the theoretical of numbers are some.
No, yeah, if your question is the discrete logarithm problem in elliptic curves and in finite fields, the complexity is not the same. The complexity in elliptic curves is quadratic with respect to the order of the group, and the other one is sub-exponential. So it was the big equation I've made. And well, the ratio of the complexity is about 12. If we do not consider a recent attack called XTNFS, so it is like 12. So this is why we use elliptic curves that have embedding degree about 12. So yeah, the point here is if there are alternates, you cannot use them in cryptography because everything that goes to the exponent. So here 0 because the target group is R with addition low. Here it is with multiplication, so it will be 1. So if you take 2 points that are linearly dependent, the pairing will be 1. So 1 to the power your secret key, so it vanishes out. So we needed to control these pairings in order to make them non-alternate. So this is where we talk about, by the way, just a very important point is that, well, the target group is fp to the power k, with k the smallest positive integer, such that the group order divides p to k minus 1. So this is very important because remember we had the elliptic curve, the discrete logarithm problem over a finite field, and then we transfer it into elliptic curves because the complexities are not the same. So with this pairing we can transfer it back to the finite field, but to the finite field to power k. So we need this k to be big enough. So that's why for example, in the NIST curve it is big. But if we want to use it in a constructive way, we want it to be small enough. The first use to control these pairings is what we call the distortion map of Verheul, is to take one of these points and to apply an endomorphism that make it linearly independent. Or you can, so this is what we call the pairing type 1. So pairing type 1 is when you have the same group and then you apply these distortion maps in order to make your points linearly independent. So at the end you will not have 1. Or type 2, type 3, so you have 2 different points, 2 different groups, but then you need to find those groups with the same order. So let's focus on the consequences. Is the problem with type 1 is you have big J1 because, well, you can prove that this type 1, those distortion maps only exist on supersingular elliptic curves because the endomorphism ring is an order in the quaternion algebra that is not abelian. But in ordinary elliptic curves, you cannot find those distortion because you can switch a Frobenius map and a distortion map. But those are details. But we have like advantages and disadvantages. And today, for example, we use type 3 pairings. We do not use type 1 pairings because of security efficiency. Type 2, they are good because you can reduce the security proof to only one group because there is an efficiently computable monomorphism. And type 3, but you cannot hash into G2. For example, if you use some protocols, for example, BLS signatures, you need to hash in G2. And there is type 3. So we were talking about the destructive use. So this is what we call the move attack and the failure attack with respect to what pairing you are using. So consider you have a public key. So a public key is Q, and your secret key is N. And P is a public point, so the generator. So if you compute the pairing between Q and P, and between, so it will be equal to P with P power n. So you have just transformed your problem of discrete logarithm problem of elliptic curves to finite field. Yeah, so the K should be big enough in order to mitigate this attack. So it was 1993, NIST will come out of us too. But then the constructive use started at 2000. So by Antoine Jou and identity-based encryption by Bonnet and Franklin. And so in our story of humans, so many think that the constructive use of fire was accidental. Someone dropped his food in the fire and he was like, well, I'm hungry anyway and I'm going to eat it and it tasted good. So this is how they discovered the constructive use of fire. So there is a nice story about Antoine Jou. So he did his pairings to improve the move and firework attack, but his paper was rejected because the reviewers were like, well, if you can do this attack in 1 minute or 2 minutes, we do not care. It is an attack at the end of the day. So he was forced to find some nice protocols in order to make his paper accepted. So, and this is one of the three-party Diffie-Hellman. So, starting from the year 2000, there was many elegant use of pairings, and one of them is the zero-knowledge proofs, or the ZK snarks that use pairings over elliptic. But the question is, can we use any elliptic curve? So we have constructions of elliptic curves. So we have the same conditions as the ones we've seen in the construction of an ordinary elliptic curve, for example, the NIST P256. But here we have this condition that the K should be not too big, not too small. Not too big, not too small. So we need to master this key. So we need to control it. But if you take a random elliptic curve, there are chances that the K will be somewhat equal to the R. So yeah, and we need this, the complex multiplication discriminant to be small enough. So this is for other reasons in order to find solutions of the Hilbert polynomial. But the idea is the third point is the most important one. So there is a nice paper by Freeman and al. About pairing-friendly elliptic curves. So this is a family of pairing-friendly elliptic curves. So I'm going to talk about two of them maybe, Cox-Pinch and MNT, because they are used recently in recursive ZK snarks, and because Cox-Pinch, I think it is the most flexible one with respect to the impedance degree, and MNT are the first ones, I think, to propose families of elliptic curves that are pairing friendly. So the Cox-Pinch strategy was, so so this third point, so you need to find K. So if you fix K, so let's say you want K equal to 12, so at the end of the day, you need to factor P to K minus 1 in order to find the R. But if you take P256, so this is very hard to factor. So the idea of Cox-Pinch is to make sure that you can find it. So you need to find a generator, so in ZRZ, and you compute T, you compute Y, you compute P, and then so in complex multiplication theory, an elliptic curve. So I haven't write it down. A complex multiplication theory verifies two equations, one with respect to the prime characteristic, that is 4p equal to t squared plus dy squared, and with respect to the order, if we call it r, it is 4r equal to t minus 2 squared plus dy squared, with the same d, with the same y, with the same t. So the idea here was to find an elliptic curve where you can master the k. But the drawback is the p is about r squared, so your new elliptic curve will have a ratio equal to 2. You will have 2 more bits in the order than in the characteristic field. But for example, in NIST, if you remember, we had about the same 256 bits. Yeah. Well, yeah. This is like this is not only related to pairing-friendly elliptic curves, but in this construction, for example, we didn't find the A and B. Yeah, we didn't find the A and B, so we need to find the A and B. There is this complex multiplication method. So the idea is just you can construct the elliptic curves with J invariant, and you know that well you can prove that those J invariants are the root of some polynomial. So you need to find find the solutions of this polynomial. So it gives you the J invariant, and the J invariant will give you the A and B. It gives you the A and B for the curve or for its twisted quadratic twist. So you have just to check if it is the curve or the twisted. So yeah, you need to verify if P plus 1 minus T times the point is 0, around the point is 0 or not. Otherwise, it will be P plus T plus 1, because the order of a quadratic twist is this. So I mean, we can prove this, but the idea is just it will be a twist or a quadratic twist. I mean, yeah. I mean, if you take an x and then you want to solve the equation with respect to y square, it will be whether on the curve or on the quadratic extension. So if you sum all the points on the curve or its quadratic twist, it will be so all the points are whether on the quadratic twist or on the curve. So the order of the twist plus the order of the curve is 2p plus 2. So we will find out that it is p plus t plus 1. But the idea is this is how you can find this elliptic curve parameters. The MNT strategy is very nice because they construct families. So all those conditions we have showed up here. So instead of doing all the computations with integers, you do them with polynomials. So you do them with polynomials, you parameterize your polynomial, and once you parameterize your polynomial, you need to find those solutions x, and then you do the complex multiplication theory as before to find the elliptic curve. So the first question of MNG, so this same idea was used by Scott Barreto, Freeman, and Barreto-Naing as well. So it is the same idea, but the idea is, so what are those polynomial you will take? What is the degree of this polynomial? So here, so remember when we were talking about elliptic curves on Z, so there is a nice theorem by Siegel that says that elliptic curves that have integral coordinates, so coordinates that are integers, are finitely many. So if you parameterize an elliptic curve here and you take t, for example, of degree 2, so you will find out, you will end up with an equation that has on the left side y squared, and on the other side some equation with x to the power 3. So this is another elliptic curve. And because elliptic curves have finitely many integer solutions, so maybe you won't find those x's that give you p prime and r prime. So you take t to be of degree 1, so you will end up with an equation that has on the left side y squared, on the right side x squared. So we know how to solve these equations. So those are Pell-type equations, or in France we call them Pell-Fermat equations, even if Fermat didn't work on these equations, so it was a mistake by Euler who attributed these equations to Fermat. So yeah, we can solve them with infinite ratios. I don't know the term in English. But the idea is, if you solve this equation with respect to x and y, so you will then have your constructions with polynomials, and then you will just iterate x until you find p that is prime and r that is prime, for example. So this same idea was used by Barreto-Naing and BLS. So it is the same idea, but they allowed a cofactor. So that is equation with a composite order. And yes, so just a nice use. So you cannot use any elliptic curve in a construction that use pairings, because you need this pairing, you need pairing-friendly elliptic curves. So zero-knowledge proofs, like ZK snarks, use those elliptic curves that are pairing-friendly. And there is a nice project going that is recursive zk-SNOG, so you do a proof for proof. So you need this condition, so finding elliptic curves that form a cycle, so the order of the one is equal to the prime character, to the characteristic of the other one. So the only elliptic curves that we know for the time being are MNT curves, but then Zixer recently have a nice construction that is only doing chains, so they use Cox-Pinch strategy, and they use the ABLS curve. So I think if you are interested, we can talk about this a bit more. So yeah, I think that is the. So I'm going to share the presentation. So these are some references, and in appendix, so you have all the shapes with the number of computations in every one. So I think that's it. If you have any questions.